Dear students, after studying this module, you shall be able to know the stereoselective and stereospecific reactions, to know the diastereoselection in the acyclic system and to predict the diastereoselection in the cyclic system. What is stereoselectivity and stereospecificity? One of the major objectives of the synthetic organic chemist is to synthesize an organic compound containing multiple chiral centers in a single specific stereoisomer. It is also desirable that the stereochemical transformations be carried out in a predictable manner so that the synthesis can be used to establish the configuration of the molecule. The stereochemistry at the chiral center during the reaction is fixed either by conducting the reaction under kinetic control, in which case the stereoselectivity depends on the difference in the free energies of the respective transition states, or by carrying out the reaction under the thermodynamic control, in which case the stereoselectivity depends on the difference in the free energies of the products. Stereoselectivity. Stereoselectivity is a property of a reactant mixture where a non-stereospecific mechanism allows for the formation of multiple product, but where one or a subset of the product is favored by the factors such as steric axis that are independent of the mechanism. Stereoselectivity is of great importance in the design of synthesis of natural products. Stereospecificity. Stereospecificity is the property of a reaction mechanism where starting materials differing only in their configuration are converted into stereoisomeric products. Thus, a stereospecific process is necessarily stereoselective, but not all the stereoselective processes are stereospecific. Stereospecificity may be total 100% or partial. The term is also applied to situations where reaction can be performed with only one stereoisomer. Stereoselective reactions. Stereoselective reactions yield predominantly one stereoisomer or one pair of enantiomers of the several diastereomers. It can also be defined as a reaction in which there is a choice of a pathway, but the stereoisomeric product is formed due to its reaction pathway being more favorable than the others available. The elimination reaction of 2-iodobutane in presence of a base tertiary butoxide in DMSO gives three products: trans-2-butene, cis-2-butene and 1-butene. The major product formation is trans-2-butene. So we can say this reaction is stereoselective because cis and trans alkenes are diastereomers. As can be seen from the reaction, the various isomers are obtained in the ratio of 60, 20 and 20%. Another example of the addition of bromine to trans-2-butene gives erythro 2,3-dibromobutane as a product. In this case, the erythro product is obtained and not formed other triodiastereomers. So we can say this reaction is diastereoselective. Stereospecific reaction. As mentioned earlier, a reaction in which stereochemically different molecules react differently are called stereospecific processes. In this case, the cis and trans stereoisomers give different products. A reaction in which stereochemistry of a reactant completely determined by the stereochemistry of the product without any other option. The addition of carbene to cis-butene and trans-butene stereospecifically gives the cis 1,2-dimethyl cyclopropane and trans 1,2-dimethyl cyclopropane respectively by the two butene systems. Principle of stereoselectivity. For a reaction to be stereoselective, the substrate must have post-erogenic elements, which in turn depends on the symmetry, or more specifically on the topicity of the reacting groups or faces on the appropriate modification, giving rise to stereoisomers, enantiomers and diastereomers. The principle of stereoselectivity, whether it refers to diastereoselectivity or enantioselectivity in a kinetically controlled reaction, is same. The two stereoisomers formed must be through two diastereomeric transitions. By virtue of their diastereomeric nature, they would differ in their free energies and thus give products in different amounts. The greater is the difference in the free energy, the higher is the stereoselectivity. A difference of 10 kJ per mole at ambient temperature leads to the formation of a preferred isomer in about 98% yield. The stereoelectronic factor, the stereo factor and the other electronic factor effects, including the participation of a chelate and hydrogen bonds, are all to be considered in designing a highly stereoselective reaction. The strategy of such synthesis has to be decided on an individual basis and no fixed guideline be given. The principle of enantioselective reaction stated above is illustrated with the help of energy diagram. Acetophenone has two enantiotopic faces, Re, Si, as shown, and an organometallic hydride represented by HMl. M is the organic ligand or ligands, can approach the trigonal carbon from either phase through two transition states, transition state 1 or 2. If the ligand is equi-energetic, R and S alcohols are formed. Racemic mixture and enantioselectivity is non-existent. But if L is chiral, the two transition states are no longer enantiomeric but diastereomeric. The stereoselectivity is achieved through the formation of the two diastereomeric transition states. It may be noted that the ground state energies of the products are same, so under the thermodynamically controlled condition, the product would be racemic. The energy level diagram of the enantioselective reaction has been well depicted here and can be seen from the given reaction pathway that how would the two different alcohols be obtained through the two different transition states. Asymmetric synthesis and asymmetric induction. According to the original definition by Mark Wald, an asymmetric synthesis is a reaction which produces optically active substances from a symmetrically constituted compounds with the intermediate use of optically active materials, but with the exclusion of an analytical process. According to broader definition by Morrison and Mosher in 1971, an asymmetric synthesis is a reaction in which an achiral unit in an ensemble of substrate molecules having either enantiotopic or diastereotopic groups or faces is converted into chiral unit in such a manner that an unequal amount of stereoisomers are produced. When the products are diastereomers, they may be either optically active or racemic. Confusion arises when reaction gives two achiral diastereomers. For example, reduction of 4 tertiary butyl cyclohexanone as shown in figure 11 to cis and trans 4 tertiary butyl cyclohexanols as depicted by the structure 12. According to the above definition, this is not an asymmetric synthesis but the analogous reduction of 2-methyl cyclohexanone as depicted by the figure 13, is since an additional chiral center is being created in the process and gives cis trans 2-methyl cyclohexanol. Asymmetric induction defines the extent of asymmetry induced at the prochiral center of substrate, either by the chirality of a reagent or by one or more chiral centers present in the substrate molecule itself. In an enantioselective reaction, asymmetric induction is equal to enantiomeric excess, and in diastereoselective reactions giving rise to the new chiral center, it is equal to the diastereomeric excess. Strategy of stereoselective synthesis. While synthesizing an optically active compound with multiple chiral centers, for example, number of natural product, one usually synthesizes the compound in racemic form, fixing the relative configuration at all the chiral centers through the diastereoselection and then applies the resolution technique. Diastereoselective reactions. Diastereoselectivity can be in the acyclic system or the cyclic system. Looking into the acyclic system, the acyclic molecules are conformationally more mobile than cyclic. The first rationalizations of the asymmetric induction worked out for reactions in acyclic systems, example Cramp's rule and Prelog's rule. We separately discuss this subject topic in the forthcoming modules. Addition of nucleophiles to the carbonyl compounds. Addition of nucleophiles to the carbonyls is one of the most common methods to generate a new carbon-carbon bond. Sato et al. In 1984 have achieved a high diastereoselectivity in Grignard reactions and a hydride addition with substrate number 15, which do not contain a chelating group but have a bulky trimethylsilyl moiety as a part of the ligand group. The syn compound Cramp product is obtained in over 99% yield. When it to ketones and the latter reduced with the metal hydride, the anti-diastereomer, again the Cramp product is obtained almost exclusively. The diastereoselective formation of methyl homoallyl alcohol has been depicted here in the given structural formulas. The diastereoselective formation of carbon-carbon double bond. Addition of halogen to alkenes. The fact that the addition of halogens to alkenes is both stereoselective and stereospecific gives an additional information about the stereochemistry of the addition and mechanism for the reaction. When the bromination of cis-2-butene gives RR and SS 2,3-dibromobutane, the bromination of trans-2-butene gives meso 2,3-dibromobutane. Is the addition of bromine syn or anti? Let us look into a deeper view by the mechanism of addition. As can be seen, the bromine adds on to the alkene system in an anti-fashion, leading to the formation of the desired products. In determining whether a stereoselective addition is syn or anti, you cannot simply look at the Fischer projections. Remember, it is often necessary to rotate about the carbon-carbon bond to get a molecule into the conformation that corresponds to the Fischer projection. What does the stereochemistry tell us about the mechanism of addition of halogen of alkenes? It can be seen that the halogen bond breaks up and the addition of the carbon-carbon double bond takes on by the concerted halonium ion intermediate. The intermediate is then attacked by the negative ion on the opposite side, leading to the anti-addition of the halogens. Hydroxylation of alkenes, formation of vicinal diol. Hydroxylation of alkene is stereoselective as well as stereospecific. Several methods of hydroxylation of olefins are available, giving 1,2-glycols. Oxidation with either osmium tetroxide, osmylation, or potassium permanganate or malic acid furnishes a syn-glycol. Mechanism of hydroxylation with potassium permanganate. First addition of M-24 in syn manner and gives the permanganate intermediate product. Oxidation of trans-alkene with KMNO4 and gives SSNRR 2,3-dihydroxybutane, and the oxidation of cis-alkene with KMNO4 gives meso 2,3-dihydroxybutane. The given figures very well explain the syn addition of the manganate ions onto the carbon-carbon double bond, leading to the formation of the glycols with the desired stereochemistry in the 2-cis and trans-alkene systems. Hydroxylation with HCOOH, formation of vicinal diol. Oxidation with HCOOH gives the opposite product, means oxidation of cis-2-butene with HCOOH gives SSNRR 2,3-dihydroxybutane, and oxidation of trans-2-butene with the given reagent gives meso 2,3-dihydroxybutane system. Mechanism of hydroxylation with HCOOH. The alkene acts as nucleophile and per acid acts as an electrophile. First, insertion of the oxygen takes place in the alkene, which gives an epoxide or oxirane kind of an intermediate, followed by the ring opening epoxide with water giving an anti-glycol. Same pathway followed with the trans-alkene, and as can be seen, the product obtained are analyzed on the basis of the mechanism of the attack of the given reagent from the opposite side and the ring opening. Per-hydroxylation. Per-hydroxylation of alkene using iodine and silver salt, which is the Prevost reaction, similarly goes through a cyclic iodonium ion, followed by the neighboring group participation to give the anti-glycol. If the reaction carried out in the presence of moisture, the intermediate acylium ion is directly hydrolyzed through route B and gives syn-glycol, which is also called as Woodward's modification. Hydroboration or the formation of an alcohol. Hydroboration of an olefin takes place in syn fashion with the boron being attached to the less substituted carbon, and the adduct on the oxidative deboronation gives an alcohol. If the double bond is adjacent to the chiral center, addition takes place to the less hindered diastereotopic phase and with the moderate to high diastereoselection. Thus, in the hydroboration of the terminal double bond in the ester 31, diismyl borane reacts from the side anti to 4-methyl, giving 4,6 product predominantly in the 87% yield. Dehydrohalogenation of an alkyl halide via E2 mechanism. E2 or elimination is stereoselective as well as stereospecific in nature. E2 is anti-elimination. Hydrogen and the halogen must be on the opposite sides of the molecule, which is anti-periplanar, before the elimination can take place. This makes sense as both the base and the leaving group is negatively charged. Therefore, they would try to be as far apart as possible. In addition, the leaving group is large and there is more routes for the removal of the adjacent proton, if it is on the opposite side from the leaving group. For example, in 1-bromo-1,2-diphenyl propane, it goes through the elimination of hydrogen and bromine in the presence of the alcoholic KOH via anti-elimination mechanism, giving E and Z alkenes, as shown and depicted here in the sequence of reactions. The mechanism of biomolecular elimination reaction is also depicted here, where the base abstracts a proton from the end opposite to the leaving group, giving the desired products. Diastereoselection in cyclic systems. Many natural products, example terpenes and steroids and alkaloids, are cyclic compounds with multiple chiral centers. Their total synthesis, and particularly those achieved during the last 4 decades, and illustrate the various strategies used in designing stereoselecting reactions in the cyclic system. Nucleophilic addition to cyclic ketones. The most extensive study has been made on the stereochemistry of the additions of nucleophiles, especially hydrides, to the cyclohexanones, cyclopentanones, and few bicyclic ketones. There are 2 possibilities: stereoselective formation of axial or the more stable alcohols, and considerable success has been had in both the directions, especially in the hydride reductions, formation of the axial alcohols. The secondary axial alcohols are generally less stable and therefore must be formed under kinetic control using bulky reagents, which prefer to approach the carbonyl group from the less hindered equatorial side, that is, the steric approach control. A large number of reagents are now available, which gives the highly stereoselective products. The results of reduction of 5 substituted cyclohexanones with just 3 of such reagents are shown here in the table. The stereoselective formation of the axial alcohols, as with the different substitutions and the reagents, are indicative here in the table. These are the structures of the stereoselective hydride transfer reagents. Formation of equatorial alcohols. Maruaka et al. 1985 and Nasipuri et al. 1984 have developed methods for the preparation of equatorial alcohols from reduction of cyclohexanones with tertiary butyl magnesium chloride using methyl alumino derivative of bis 2,6-di-tertiary butyl 4-methyl phenoxide, and reduction with fluoroenyl oxy-aluminium dichloride. Reduction of 1-camphor. Reduction of 1-R-camphor by 1 equivalent of lithium aluminium hydride afforded a 90.2:9.8 mixture of isobonienol with borneol, and 88.7 to 11.3 ratio was obtained with the racemic camphor under identical reaction conditions. A category of diastereoselective processes involves the coupling of 2 compounds at the prostereogenic centers with the formation of 2 new stereocenters, as may occur with the aldol and Michael reactions. The focus of concern here is with the stereochemical relationships between these centers, that is, simple stereoselectivity. In summary of this module, we have described the overview of stereoselective synthesis with the ample amount of illustrations to make it readily understood. Stereoselectivity has been classified under 2 categories: enantioselectivity and diastereoselectivity. Stereospecific reactions are reactions in which stereochemically different molecules react in different ways. In this case, the cis and trans stereoisomers give different products. Stereoselective reactions are the reactions that yield predominantly one stereoisomer or one pair of enantiomers of several diastereomers. We have discussed the diastereoselection in an acyclic system with carbon-carbon and carbon-carbon double bond, and we also have discussed the diastereoselection in cyclic compounds mainly on the basis of axial and equatorial positions of the substituent, and has been illustrated by the reactions such as nucleophilic addition of cyclohexanones and other suitable substrates.